Hello students. So what have we done so far? We've solved trig equations of the form sine equal to a constant, cosine equal to a constant, or tangent equal to a constant. So things like trig function equal to a number. Well, we're also able to do algebra. In addition to solving those equations, we should be able to solve more complicated ones. Equations like, how about 3 times the sine of x plus 2 is equal to 1? And the argument will be pretty straightforward. Do you think you could solve that for sine of x? Yeah, of course you could. Right? All you need to do is subtract 2 from both sides, giving you 3 times the sine of x equal to negative 1. And then you need to divide both sides by 3, giving sine x equal to negative 1 over 3. Nice. So this is now a simple trig equation. That's a trig equation of the form trig function is equal to a constant. So we know how to solve those. So if we want to solve that, we can reference that flowchart, and we see the solutions. So the solutions are sine inverse of negative 1 over 3. Let's see, so basic solutions. Pi minus sine inverse of negative 1 over 3. And so the general solution is just going to be those two plus 2 pi k. Sine inverse of negative 1 over 3 plus 2 pi k, and pi minus sine inverse of negative 1 over 3 plus 2 pi k. Now there's one bit of simplification you can do. So picture the graph of inverse sine in your head. It's odd, right? You can use that sine inverse is odd. So this negative sign I could pull out front, getting a simpler general solution, negative sine inverse of 1/3 plus 2 pi k, and pi, this negative sign would pull out front to cancel with that negative sign, pi plus sine inverse of 1 over 3 plus 2 pi k. Let's tidy that up a little bit. Nice. So the remainder of this document is just a sequence of increasingly, complicated trig equations, each of which you can reduce to simple trig equations, and then solve those simple trig equations. For instance, if you want to solve 5 times the tangent of x plus 2 is equal to 1, well, again, that's easy to solve that for tangent. 5 times the tangent of x equals negative 1. Subtract 2 from both sides, giving you tangent of x equal to negative 1/5. Then you recall how you solve tangent of x is equal to a constant. You only need one basic solution, then you add pi k. So I see tangent inverse of 1/5, negative 1/5, plus pi k, or simplified, right, inverse tangent, picture its graph, look at the graph of inverse tangent. It's odd. That'll give you negative tangent inverse of 1/5 plus pi k. Either of those are answers that I would be happy with. If you want to find all of the solutions to 2 times the sine of x minus 5 sine of x plus 2, well, we'll follow the same steps. First, let's solve for sine of x. And maybe in order to simplify some of this walk, maybe I'll set s equal to sine of x to make the equation that I need to solve simpler looking. The equation that I need to solve will be 2s squared minus 5s plus 2 equals 0. Well, that's a quadratic equation. Quadratic equations, you know how to solve those. You can factor it if you want. You can complete the square if you want. You can use the quadratic formula. I'll use the quadratic formula. So using the quadratic formula, we will get s equal to negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. And, well, whenever you use the quadratic formula, the answer looks more complicated than it needs to. We can actually compute all this stuff. So let's see. 4 times 2 is 16. 25 minus 16 is 9. Square root of 9 is 3. So let's do that much work just automatically. So that's 5 plus or minus 3 all over 4, giving me 8 over 4, or 5 minus 3 is 2, 2 over 4. So that's s, not x. S is equal to 2 or 1/2. All right, so we have sine of x equal to 2, sine of x equal to 1/2. That gives us two simple trig equations, both of which we now need to solve. Well, the first one, sine of x is equal to 2. 2 is bigger than 1. It's not in the range of inverse sine. So sine of x equals 2 has no solutions. On the other hand, sine of x equal to 1/2, let's find the solutions to that. And think for a second, is 1/2 an output that you remember seeing on the unit circle? It is, isn't it? So let's draw a unit circle. So let's see. There's this angle of pi over 6, which corresponds to the point root 3 over 2, 1 over 2. There's one solution. So the solutions that you see on the unit circle, pi over 6, and this one over here at 5 pi over 6. So that means that we can read off now all of the solutions by just adding 2 pi k's. So the full solution is x equal to pi over 6 plus 2 pi k, and x equal to 5 pi over 6 plus 2 pi k. Nice. So if this were a live lecture, I would not be doing all of these examples. I would be pausing periodically and saying, well, I'm going to save my breath while you guys do some, while making vocal sips on my beverage, which right now is a nice barley tea, which simulates the taste of coffee. And I would have you guys do them, but I can't do that. So here's what I encourage you guys to do. Go through and solve these equations. Do your best to solve them to the best of your ability, and then come back and watch this video, see if they agree. Let's go ahead and do it. So let's keep on going. 6 times the square of the cosine of x minus 5 times the cosine of x plus 1 is equal to 0. Let's try to solve that. Step 1, solve for cosine of x. Let's go ahead and set cosine of x equal to c, just so I don't have to write cosine so many times. That will give me 6c squared minus 5c plus 1 equals 0. And again, you could try completing the square, you could try factoring. I will resort to, I think, the quadratic formula. Right, just because it's a non-monic polynomial. This leading coefficient is 6 instead of 1. So by the quadratic formula, I'll see solutions at c equal to negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. So walking that out, that looks like, let's see, 4 times 6 is 24. 25 minus 24 is 1. Square root of 1 is 1. So this will be 5 plus or minus 1 over 2 times 6 is 12. 6 over 12, or 4 over 12. That's 1/2, or 1/3. both of those outputs are valid outputs for cosine. They are numbers between -1 and +1, so each of those will have solutions. And in fact, again, looking at the unit circle, if you look at pi over 3, you will see an x value of 1/2, a y value of √3/2. So there's one of the solutions. And the other one, depending on how you think, if you go in the negative direction, negative pi over 3, you'll see a solution. Or if you go all the way around to 5 pi over 3, you'll see a base solution. And maybe just for emphasis, I'll write down what you would get out of using each of those. 1/2 comma negative √3/2. So So let's start with cosine of x is equal to 1/2. So my basic solutions are pi over 3 and negative pi over 3. Maybe for emphasis, I'll put here or 5 pi over 3. So since these two numbers, their difference is exactly 2 pi, so they somehow correspond to the same point on the unit circle. They both correspond to this point. So regardless of which one of those you use, you'll get the same infinite family of solutions. So they're the basic solutions. The general solutions is pi over 3 plus 2 pi k, and pi over 3, not pi over 2, negative pi over 3 plus 2 pi k. And again, for emphasis, in green, you'll have the same infinite family of solutions if you write 5 pi over 3 plus 2 pi k. Alright, so that solves half of it. The other half is cosine of x is equal to 1/3. 1/3 is not an output that you see on the unit circle, so you just have to use inverse trig functions. So the other infinite family of solutions is cosine inverse of 1/3 plus 2 pi k, and negative cosine inverse of 1/3 plus 2 pi k. So that tells me the full infinite family of solutions. It's pi over 3 plus 2 pi k, negative pi over 3 plus 2 pi k, cosine inverse of 1/3 plus 2 pi k, and negative cosine inverse of 1/3 plus 2 pi k. Nice. So again, we'll just keep on going. Let's solve more trig functions. You can have complicated things going on involving the trig function, and also complicated things going on the inside of the trig function. So let's try to solve this equation. 3 times the tangent of 2x minus 1 plus 2 is equal to 1. So step 1, I'll solve for the tangent of 2x minus 1. And as I've done in the past couple, I'll set t equal to the tangent of 2x minus 1. That will give me 3t plus 2 equals 1. So t is equal to, subtract 2 from both sides, you get minus 1, divide by 3, negative 1 over 3. So tangent of 2x minus 1 must be negative 1 over 3. Well, that's the type of thing that I can use inverse trig functions to figure out. So I see tangent of some input, which is in blue, is equal to negative 1 over 3. If I want to solve for that input in blue, all I have to do is apply inverse trigonometry. I'll get 2x minus 1 equal to tangent inverse of negative 1/3 plus pi k. Although maybe it's helpful to simplify. Tangent inverse is odd, so that's the same thing as negative tangent inverse of 1 over 3 plus pi k. Nice, so that means that 2x minus 1 is equal to negative tangent inverse of 1 over 3 plus pi k. Does that look like you can solve that for x? Yeah, of course you can. Add 1 to both sides, then divide by 2. So I guess doing that one step at a time, 2x is equal to negative tangent inverse 1 over 3 plus pi k plus 1. Right, you add this to the other side. Next we'll divide by 2. X is equal to negative tangent inverse of 1/3. Maybe I'll interchange the order of these two so the thing with the k in it is the last thing. Plus 1 plus pi k all over 2. So you can still solve trig functions where there's something complicated going on inside and outside of the parentheses. Alright, so all of the previous examples have been complicated trig equations, but they've only involved one trig function. So what if I give you a trig equation that involves multiple trig functions? Let's try to solve this one. 4 times the cosine of x plus 5 is equal to 4 times the square of the sine of x. And you know what? We haven't done any of this so far in this particular note packet, but let's see if we can even visually see where the solution should be. Well, we should be able to see that by graphing both sides of the equation and seeing where those two functions cross. So let's go ahead and do that. I'll do that off to the side. Alright, so here are the graphs of the two ingredients. It looks like there are some points where they cross, right? There's it's like there's a point of intersection, there's a point of intersection, there's a point of there are lots of points where they touch. And maybe we even see something. We see that it looks like when they touch, they kind of bounce off each other. They don't go straight through. They lie tangent to each other at those points of intersection. So it looks like there are solutions. Let's try to find them. All right, so step one is, well, we want to apply the techniques we've developed so far. But those techniques only work if you only have a single trig function floating around. But I see two trig functions floating around. I see a cosine and I see a sine. Oh, but notice, I can express sine squared in terms of cosine, right? I know that sine squared of x plus cosine squared of x is always equal to 1. As a consequence, the sine squared of x should always be the same as 1 minus cosine squared of x. So making that substitution, this equation will become 4 cosine x plus 5 equals 4 times 1 minus cosine squared of x. Distributing the right-hand side, I guess, I'll get 4 minus 4 cosine squared x. And so I want to set this equal to this and see what the solution is. Well, I guess, right, if I want to follow this model, I want to put everything on the same side. Maybe I'll put everything on the left-hand side, and I'll also set cosine of x equal to c. So let's see. I'll start by adding 4c squared to the other side, plus 4c from this, plus 5, and I'll subtract 4 to the other side, plus 1. That's something that you'll even recognize factors. That's 2c plus 1 squared. If you don't believe me, then check by FOILing. So as a consequence, it looks like I get c equals 0. So that means c is equal to negative 1/2. So I just get cosine of x is equal to negative 1/2. And so now what do? You look for elementary solutions, and then you add some 2 pi k's. But negative 1/2 is a number that you see on the unit circle. You see it right here, I guess. So at 2 pi over 3 and at 4 pi over 3. Groovy. And some of you who followed a different algorithm may instead of writing this, instead you had negative 2 pi over 3 plus 2 pi k. But that would give the same infinite family. So both of those results would be correct. One last example. Let's try to solve the equation. The square of the tangent of x plus the square of the secant of x is equal to 1. And there are a few strategies you might use. There's a relationship directly in Tom that tells you how secant squared and tangent squared interact. But I'm going to maybe follow the strategy that I understand sine and cosine really well. So I'll just try to write everything in terms of sine and cosine, and I'll see what things simplify down to after I do that. So doing that, let's see what we get. Let's re-express everything in terms of sines and cosines. So tangent is sine over cosine. So that'll give me sine squared x divided by cosine squared x plus 1 over cosine squared x is equal to 1. So, simplify it down as much as we can. That will give me sine squared x plus 1 all over cosine squared x is equal to 1. And I know it says to simplify down here, and what I just did was a bit of simplification, but you know what, that's okay. Let's keep on simplifying though. I see a fraction on the left-hand side of that equation. It's annoying to see a fraction on the left-hand side of the equation. Let's rewrite that as sine squared x plus 1 is equal to cosine squared x, cross-multiplying. All right, so again, this involves both sines and cosines. So let's try to make it so it doesn't involve both sines and cosines. How can I do that? Well, I can either rewrite sine as 1 minus cosine. So I'll re-express it using only sine. So that means I'll want to get rid of this cosine. So what do I know about sine and cosine? So this is something that you know about sine and cosine. Sine squared of x plus cosine squared of x is equal to 1. And if there's one thing that you should definitely, no matter what, always remember about trig functions, forevermore, it's that fact. Can you solve that for cosine? Because if you can solve for, rather, cosine squared, if you can solve for cosine squared, then you can get rid of that cosine squared. So let's do that. So it will reduce to cosine squared of x equals 1 minus sine squared of x. So I'll make that substitution. I'll replace cosine squared of x with this. So that will give me sine squared x plus 1 is equal to 1 minus sine squared x. Looks like I need to solve, so let's see, I'll add sine squared to the other side. So it'll give me 2 sine squared x, and I'll subtract that 1 over to the other side, equals 0. So it looks like I'm down to sine, well, that's easy to solve for sine, right? Sine x equals 0 is the equation I end up with. So the equation that I wind up with is the equation sine of x is equal to 0. And, well, does that look easy to solve for sine? So we'll follow the same strategy. Is 0 an output that you see on the unit circle? Yeah, sine of 0 is 0, and sine of pi is equal to 0. So I'll give you my two basic solutions. And now I'll add 2 pi. That'll give me x is equal to 2 pi k, or x is equal to pi plus 2 pi k. And let's actually look at those, because I think that that family of solutions will simplify. So let's list these. So it looks like when k is 0, I get 0, 2 pi, 4 pi, 6 pi, and so on. That formula will give me pi, 3 pi, 5 pi, 7 pi. So listing them in order, I'll see 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi. That's any multiple of pi. I get the family of solutions given by x is equal to any multiple of pi, x equal to pi k. And you know what? Again, let's see if this looks reasonable by graphing the thing. I think I still have the graph up. Let's pull that down. Let's graph the solutions to that. So tangent squared of x plus secant squared of x is equal to 1. So let's graph tangent squared of x plus secant squared of x. And, well, okay, so there we go. We see the graph. And you know what, just for laughs, I want to know when that's equal to 1, so let's explicitly draw the line at y equals 1. Oh, it looks like it's unwilling to draw the line at y equals 1. Oh, well. So let's just take a look at this graph and see where we see a y value of 1. So there I see a y value of 1 at 0. There I see a y value of 1. That's somewhere a little bit bigger than 3. Yeah, that could be pi. Somewhere a little bit bigger than 6. Yeah, 2 pi. So I see 0, pi, 2 pi. Notice we also see, a solution at negative pi, negative 2 pi, and so on. Great. So I hope you've enjoyed this lecture about solving trig equations. I'll see you with the next one. Talk to you later.